So in this video, I'm going to work out 3 problems for you that involve the material we're studying in this unit with force diagrams, sums of forces equations, and solving those with numeric values. You don't have this worksheet, but here are a few of the problems. So if you want to, you can pause the video here and sketch this cartoon out and jot down the questions and the information given so that you can work along with me. So pause now if that's what you need to do. All right. So here's my man. He's pushing this lawnmower. The lawnmower's 15 kilograms and he's pushing it with 120 newtons of force on that handle, which is at a 35-degree angle. So I'm going to make a big force diagram for the lawnmower. All right, I'm going to start out drawing my X and Y axes. The dot there represents the lawnmower. I've got the force of gravity of Earth on the mower. I have a normal force of the ground on the mower pushing up. I have that push from the handle that's going to be directed here. I'm going to just call that F applied, man on mower. And that 35-degree angle, if you think about it, that's 35 degrees there, which matches that 35-degree angle. And so in geometry, those opposite angles are congruent. So that's my 35-degree angle right there. All right, and then let's see. That's really all I know right now. I'm not sure. Oh, it does say it pushes across the lawn at constant speed. So I think what I'm going to need to do is think about splitting up this applied force into its X component. I'll just call that F applied X, and I'm going to call F applied Y this purple arrow, and I'll just put it below FG. Now if the lawnmower is moving at constant speed, that means the forces on it are balanced, and you see that F applied X right now doesn't have a force opposing it, but it needs to have one. So that tells me that I'm going to need to include friction here. And that friction is by the ground on the mower. So in terms of equalities, I think what I'm looking at in this working force diagram is I have my F applied X equal to my friction, and I have that normal force on top equal to the sum of gravity plus F applied Y. All right, so once you feel like you have your force diagram drawn out, labeled, and the working diagram's ready to go, the next question is to calculate the horizontal component of the force you apply. In other words, what is F applied X? So I'm going to have to write, let's see, this is some trig. I'm going to have to figure out F applied X. I don't know friction, so I can't get F applied X, but I know that this applied force here is 120 newtons. So if I think about my trig, here's my original F applied, 120 newtons. This is my F applied X, and then here is F applied Y. And that 35-degree angle is right there. So all I've done is to redraw this triangle down here. I need the X component, which is adjacent to that 35-degree angle. So that's going to be the cosine of 35 degrees is F applied X over the hypotenuse, which is 120 newtons. You can cross multiply here and solve. F applied X is equal to 120 newtons times the cosine of 35. Make sure you're in degree mode, remember. And you're going to get 98.3 newtons. And when I look at my force diagram, since F applied X is to the left, it's going to be a negative 98.3 newtons. Part C asks, how does the size of that horizontal component compare to the size of the friction force on the lawnmower? Well, if you go back to your force diagram up above, you'll see the answer. I know that these two forces have to be equal to one another, so friction is going to be a positive 98.3 newtons. They're equal. And I know why is because the problem tells me that I have constant speed. And that means that all the forces acting on the lawnmower must be balanced, or in other words, my net force is 0. For part D now, we have to write an equation for all the vertical forces on the lawnmower. When you're working in the vertical direction, we're going to look here, always go back to the force diagram. I'm going to write the sum of forces in the y. And you just get them right off the force diagram. So up here I have the normal force, I have the force of gravity, and I have F applied y. And the sum of those forces is 0. In part E, we're going to be asked to use that sum of forces equation, and we're going to find the normal force. If this is my unknown, I should be able to calculate the force of gravity on the lawnmower and the applied force in the y direction on the lawnmower. So I'm going to go ahead and work on that. Just over here on the side, let's calculate the weight of the lawnmower. It tells me in the question that it's a 15 kilogram lawnmower. And remember, our conversion is 9.8 newtons per kilogram. So the weight of this lawnmower is 15 times 9.8. That gives me 147 newtons. And because gravity is a downward force, this will be a negative 147 newtons. To find F applied y, I'm going to make use of this triangle here again in part B. This time I need that y component. This y component is across, or the opposite side to the 35-degree angle. So when I do my trig work, I'm going to do the sine of 35 degrees is the opposite side over the hypotenuse, which is 120 newtons. Again, you can cross multiply. Make sure that you're in the degree mode again. So 120 times the sine of 35 gives me 68.8 newtons. And F applied y is a downward force also, so it's going to be negative 68.8 newtons. I'm running out of room here, sorry. I'll draw you a little line right there. Whoop. So now I've got my equation set up. I just need to isolate the normal force. I'm going to add these two onto the opposite side. And what you end up with is the normal force is equal to 147 plus 68.8 newtons. Get a total of 215.8 newtons for your normal force. Okay, so when we go back to make a quantitative force diagram, I'm going to take one more unique color. My normal force here is 215.8 newtons. The force of friction was 98.3 newtons. The force of gravity, the weight of the lawnmower, was negative 147 newtons. The force applied y is negative 68.8 newtons. I'll squeeze that in right there. And the applied force in the x direction up here in part B was negative 98.3 newtons. And so you can see what we ended up with is F applied x is equal to friction. So the horizontal forces are balanced. And in the y direction, the normal 215.8 newtons is equal to the sum of the force of gravity and the force applied y if you add those two forces there together. And then we can label the original force 120 newtons applied force along that 35-degree angle. So that's the first problem. I'm going to start the second one here. Give you a second if you need to pause the video so that you can sketch this problem and draw the skier going down the hill. Pause now. Right, in this problem, we're only asked to find a quantitative force diagram. The skier's mass is 80 kilograms, so we need to start with that force diagram. Remember that on the angle, this surface here of the slope, this is our x-axis. So I'm going to draw a parallel line there and label it x. The y-axis is always perpendicular to the x-axis. So when we think about the forces that are involved here, let me switch colors again. The skier is represented by the dot. The force of gravity pulls the skier straight down towards the center of the earth. The normal force is the force of the slope pushing up on the skier, so it pushes up perpendicular to the surface along the y-axis. We'll call that ground on skier. And we know that the skier races down the slope at a constant speed. So that tells me that this force of gravity is going to have an FGX component and an FGY component. If the skier's moving at constant speed, that means that the forces are balanced on the skier. So normal and FGY are equal to one another. They add up to 0. I've got to have a force to offset this FGX. That's going to be friction. So I'm going to add friction there. I'm going to call that ground on skier as well. Okay, and I'll mark that one equal. Now, to solve this, you have to figure out where you're going to put this 25-degree angle. And sometimes that's really tricky, but I can give you a rule of thumb that will always work for force diagrams that are slanted or rotated the way this one is. This angle will always show up between FG and FGY. So my 25-degree angle is going to be right there. What happens is, if this angle was 0 and the skier was flat on the ground like here, the y-axis would be here and the x-axis would be here. But we've lifted the skier up 25 degrees. So essentially what you've done is rotated your y-axis from completely vertical to 25 degrees from that. And that gives me that angle as 25 degrees. So you can go by that rule of thumb, or remember how that visual works, that you're shifting the axes of the force diagram by the amount of that angle. All right, let's get to work on the quantitative part. I'm going to start with the weight of the skier. His mass is 80 kilograms, so I'm going to multiply that by 9.8 newtons per kilogram. 80 times 9.8 gives me a weight of 784 newtons. Okay, so that's my FG. This force is not positive or negative because it's in between the axes of the graph, so I'm just going to list it as the numerical value, not positive or negative. I do have this angle, and so I can do some trig to find FGY and FGX. If you look at FGY, it's adjacent or next to the 25-degree angle. So I'm going to do a cosine function. 25 degrees is equal to the adjacent over the hypotenuse, which is the 784 newtons. So FGY, if you cross multiply, 784 times the cosine of 25 gives me a value of 711 newtons. And FGY is in the negative y direction, so I'm going to make that negative. Now, if you have FGY is negative 711 newtons, I know that the normal force is going to be the opposite direction of that, but an equal value. So the normal force here is going to be positive 711 newtons. Next, I need to find FGX. I'm going to switch colors here. I'll use orange. To find FGX, I'm going to slide that vector to right here. Those two lines are parallel to one another, but it closes up the FG triangle. Now FGX is opposite or across from that 25-degree angle. So I can do a sine calculation. The sine of 25 is FGX over the hypotenuse of 784 newtons. So if you multiply that out, 784 times the sine of 25, you get 331 newtons. And since FGX is in the positive direction or to the right, it's going to be positive 331 newtons. Friction then is equal and opposite to that. That's going to be the negative 331 newtons. And with that, we have created a quantitative force diagram, and we labeled all of our forces and the components in that working diagram. All right, here's the last problem, number 3. Take a minute again, pause here if you need to write this problem down and sketch the drawing. All right, here what we're going to do is draw a force diagram that will help us answer the questions that are given. We need to find the tension in the rope, which is this dark solid line here, and we need to find the angle marked in the diagram, which is the theta here. Part of that got cut off. Sorry about that. Right? So let's draw the force diagram for this bucket right here. It's hanging flat. So I'm going to draw my axes for the force diagram like that. I'm going to represent the bucket with a dot in the center. I know that the force of gravity acts on the bucket. I know that there's a 15 Newton pull on the bucket straight to the left because it says the pull is horizontal. I'm just going to call that F applied. Call it person on bucket. And then I know that this rope that's holding the bucket is at an angle, so I'm going to draw that applied force or tension force at the same angle that it is in the sketch. And I'll call that rope on bucket. Now the bucket's hanging from the ceiling, so there's no normal force here. My force diagram is complete. If we want to make this into a working diagram, we're going to need to split this force of tension because it's angled into an FTX component and an FTY component. That tension is kind of in a northeast direction, so there's a north component and there's an east component. And the angle that I don't know is that one right there. Okay, so let's label what we know. I know that the pull on the bucket is the 15 newtons. Because it's pulling to the left, I'm going to label this negative 15 newtons. I know that the applied force and the FTX are equal to each other because the bucket is just hanging there. It's in a still type of position. It's not accelerating or moving at all. So if the applied force is negative 15 newtons, FTX is positive 15 newtons. And we have a 5 kilogram bucket. So I should be able to go down here and do the weight calculation, convert my 5 kilogram bucket mass into a weight in newtons. 5 times 9.8 is 49 newtons, and since that's a downward force, it's going to be negative. I know that FG is going to be equal and opposite to FTY. The sum of those forces is 0. So my FTY component is going to be positive 49 newtons. We need to calculate the tension in the rope. Well, the nice thing about this is I'm looking for FT. I know FTX is 15 newtons and I know FTY is 49 newtons. If you remember back to some geometry with your triangles, in order to find the third side of the triangle, which FT is the hypotenuse, I can use the Pythagorean theorem. FTY squared plus FTX squared equals FT squared. So I'm going to plug in my values. I find a lot of times the trickiest part of this is remembering to take the square root of your answer when you're finished. So make sure you do that. You get a value for the tension as 51 newtons, which makes sense for a triangle because the hypotenuse has to be longer than either side. I know FT is the hypotenuse because it's the original force. The original force of tension is larger than the X or the Y component. So that's a sensible answer. Now the last question is a little bit trickier. Figure out the measure of that angle that's marked here in the cartoon or in the force diagram. I'm going to use some inverse trig to do that. You know FTY, you know FT, and then FTX can be represented just by sliding it up from this location on the x-axis to this dotted line that I just drew in. So I'm going to do inverse sine of theta is equal to the sine of this angle is the opposite side, which is 15 newtons, over the hypotenuse, which is 51 newtons. In your calculator, you're going to do the second function and then sine. Here, I'll show you again. If you hit the second function button and then sine right here, you'll get sine to the -1. It's waiting for you to put in the values. So I'm going to type in the 15 divided by 51. And as long as you're in degree mode, this should work out. You get an angle of about 17 degrees. And that's the angle of that rope from the horizontal, or sorry, from the vertical. So I'll label that as 17 degrees. And that's the end of that problem. So I hope these examples help you. We solved, if you go back and look, our first problem was an object on a flat horizontal surface, but there was an angled force, and we used some trig and sum of forces equations to solve for each part of the force diagram. The skier problem that we did second had an object on a slanted surface, so we had to rotate our force diagram to match that slant, but again we used some trig and our understanding of balanced forces to figure out what the value of every force was. And then finally I had an object that was hanging that had a rope that was at an angle, and we used some Pythagorean theorem and inverse trig that we had not used before, again, to figure out the value of every piece of a force diagram. So that's a good way to solve force diagrams. Always start with a good drawing and then start thinking about how you can work through trig functions, sine, cosine, and tangent, or working through sums of forces equations to get at the values that you're looking for. Thanks.